Hey everyone, welcome back. Today, we're diving deep into the invisible world that, believe it or not, holds our most powerful machines together. We are talking about static force analysis. It's the secret sauce, the engineering magic that stops a massive engine from just, well, tearing itself apart. All right, let's get right into it.
So just look at this crankshaft. This thing is built to handle absolutely gigantic forces from explosions thousands of times a minute. But how? Seriously, how do you even begin to calculate and control the incredible stresses that are just flowing through every single part? That is the big question we are going to answer today.
So, to get started, we've got to learn the language engineers use to even talk about these forces. We're heading right inside the machine to make the invisible, well, visible. Okay, so static force analysis, this is the absolute bedrock of machine design. The whole idea is to analyze a machine as if it's frozen in a single moment in time. No acceleration, just perfectly still. By doing that, engineers can see all the forces in a perfectly balanced state. This is how they make sure that for any load you throw at it, the machine is strong enough to handle it safely and reliably. It's what prevents catastrophic failure. So how do you get to that perfect balance? Well, it all boils down to one single fundamental principle. You can think of it as the golden rule that governs everything we're about to talk about. And that rule is static equilibrium. This is the goal, always, for any single part of a machine. Every push, every pull, and every twist has to be perfectly canceled out by another. It's like a cosmic tug-of-war where nobody wins. If all those forces add up to zero, the part doesn't accelerate. It's stable. It's safe. It's in equilibrium. And here is the math behind the magic. These three surprisingly simple equations are the keys to the entire kingdom. The first one basically says all the forces pushing left and right have to cancel out. The second one says all the forces pushing up and down have to cancel out too. And that third one, that deals with moments, which is really just a fancy engineering term for any twisting or turning force. For a part to be stable, all those twists and turns have to balance out to zero as well. That's it. That's the core of the whole analysis. Now, you can't just apply those rules to a whole engine at once. That would be crazy. The secret is to break the machine down into its simplest little pieces. So let's add a couple of key components to our engineer's toolkit. Check these out. These are basically the two fundamental building blocks engineers work with. On the left, you've got a two-force member. For this thing to be in equilibrium, the two forces acting on it have to be equal, opposite, and they have to pull straight along the line connecting them. Think of a simple rod. Then on the right, we've got a three-force member. The rule here is a little different. For the forces to balance, their lines of action have to all cross at one single point. Just knowing these two simple patterns makes analyzing a super complex machine way, way easier. Okay, our toolkit is officially assembled. We've got the rule of equilibrium, and we've got our two basic building blocks. So now, let's put it all together and see how this works on a real-world example. We are going to analyze this, the slider crank mechanism. You find this thing everywhere, in pretty much every internal combustion engine, in a ton of pumps. Its whole job is to turn the back and forth linear motion of a piston into the spinning rotary motion of a crankshaft. So we're going to solve the puzzle of the forces inside this thing by following a really logical three-step process. First, we'll start with the piston, then we'll move to the connecting rod, and we'll finish up at the crank to figure out the exact torque needed to keep the whole system in balance. Step 1, we use an absolutely critical tool, the free body diagram. What we do is we mentally cut out just the piston, and we draw only the forces acting directly on it. So we've got the gas pressure P, which we know, but then we have two unknowns, the force from the connecting rod pushing back and the force from the cylinder guide holding it in place. Now, because this piston is a three-force member and it's in equilibrium, we can actually solve this puzzle visually with a neat trick. We know the exact direction and strength of the gas pressure, P. And we also know the directions of the other two forces, right? One acts along the connecting rod, and the other is perpendicular to the cylinder wall. So we can draw these forces as arrows, placing them head to tail. And since they all have to balance out to zero, they have to form a perfect closed triangle. By just measuring the lengths of the other two sides, we can find the exact magnitude of those unknown forces. It's such an elegant graphical solution. So here's the crucial link. That force we just figured out, the one from the connecting rod, gets transmitted right along that rod. It flows from the piston through the rod, and now it's pushing directly on the crank, trying its hardest to make it turn. And that brings us to the final piece of the puzzle. That force from the connecting rod, along with the reaction force from the main bearing where the crank pivots, creates what engineers call a couple.
Now, a couple is just a pair of equal and opposite forces that aren't lined up, so they create a pure turning effect. To keep our whole system in that perfect state of static equilibrium, we have to apply an input torque, T, that creates a turning effect that's perfectly equal and opposite. And just like that, the entire mechanism is balanced.
So far, we've only been talking about balancing forces in a static, frozen moment. But real machines, they're dynamic. They also have to balance flows of energy. And this brings us to a really cool component that handles the energy side of the equation, the flywheel. A flywheel is, for all intents and purposes, a mechanical battery. Its job has nothing to do with balancing forces. It's all about managing energy. In an engine, for example, the power stroke delivers this massive punch of energy all at once. The heavy flywheel soaks up all that excess energy, storing it as rotational momentum. Then it releases that energy smoothly during the other non-power strokes to keep the whole engine spinning at a nearly constant speed. Now, it's really easy to get flywheels and governors confused, but their jobs are totally different. Remember, a flywheel smooths out the speed variations within a single revolution. A governor, on the other hand, is what regulates the engine's average speed over many cycles. It does that by adjusting the fuel when the external load changes, like when your car starts going up a hill. So how smooth is smooth enough? Well, it really depends on the machine. This table is pretty cool. It shows the coefficient of fluctuation of speed for different types of machines. And just look at the difference. A big crushing machine can be pretty jerky and rough with a value of 0.2, but an electrical generator, it has to be incredibly stable with a value as low as 0.002. The flywheel's size and weight are designed specifically to hit these targets. Okay, so let's tie this all together. It's kind of amazing, right? Starting from just a few simple rules of equilibrium and an understanding of a couple of basic components, engineers can build a complete picture of all the unseen forces churning away inside a machine. This is what allows them to control absolutely massive pressures and manage huge surges of energy, all to make sure our machines run smoothly, efficiently, and most importantly, safely. So the next time you see a piece of construction equipment, or even just look down at your bicycle pedals, take a second look. Now that you know what to look for, can you see the engineering principles we talked about today? Can you spot those simple 2-force and 3-force members, quietly controlling all the complex